Hey everyone, welcome back to Linear Algebra. This will be lecture 10 of the course. In this section we're going to explore determinants and its relationship to row reduction. And so we saw previously in the last section when we introduced the determinant that the computation of the determinant can be very taxing as the dimensions of the matrix grow. And so really kind of the main point of this section is to introduce a different way to calculate the determinant that is most of the time advantageous computationally, particularly for large matrices. Right, so the cofactor expansion method that we talked about previously is sort of the formal definition of the determinant, but there are other ways to get to the determinant that may be more computationally efficient. And so our method is going to primarily involve row reducing a matrix and then using the reduced matrix to calculate the determinant. Okay, so let's go ahead and jump into it. So we'll call this section 3.2 Determinants and Row Reduction. All right, so as I said, the basic idea is given a matrix A, given a matrix A, what we'd like to do is we'd like to know how does the determinant of A compare to the determinant of the reduced row echelon form of A. All right, so what happens to the determinant as we apply row operations to a matrix, right? And so just kind of in order to get to sort of the punchline immediately, we're gonna look at the following theorem, which details the determinant of a triangular matrix. Okay, and I think when you see the theorem, you'll say, you'll be able to tell without me even saying kind of where we're headed here. All right, so here's the first theorem that we'll need here. So we're gonna let A be an upper triangular n by n matrix. So let A be an upper triangular n by n matrix. Okay, then the determinant of A is going to be equal to A11 times A22 times ... times ANN. Okay, so the determinant of an upper triangular matrix is essentially the product of the entries of the main diagonal. So the determinant is the product of the entries of the main diagonal. Now notice this is just for an upper triangular matrix. This is not for any old matrix, obviously. Otherwise, we would have never defined the determinant as we did. But if I have an upper triangular matrix, so let's see an example. Let's let A equal the matrix 2, 3, 0, 1, for example. Now what this is saying is that the determinant of A is equal to 2 times 1. Well, in this case, we can easily confirm that by using the original method, which would have been 2 times 1 minus 0 times 3, right? So, of course, we do get 2, right? But this is going to work in general for upper triangular matrices. So a more interesting example would be the following. Let's let A equal 1, 2, 3, 0, 1, 2, 0, 0, 1. Okay, in this case, the determinant of A is equal to 1 times 1 times 1. Right, it's just the product along the main diagonal. Now we can confirm this by calculating the determinant using the cofactor expansion method, just to make sure that we get the same answer. And so recall that that's going to be A33 times script A33 plus A32 times script A32 plus A31 times script A31. Okay, and so A33 is 1, and then it's -1 to the 3 plus 3 power times the submatrix that you get when you remove the third row, third column. So that would be 1, 2, 0, 1. And then the other two, these two, A32 notice is 0 and A31 is also 0, so you're going to get zeros there. And so what happens here? Well, this is 1 times 1, so it's really just this determinant here. And we can see quickly, just using the formula for a 2 by 2, that this is 1 minus 0. Okay, and so you can see that they agree. Right, and that's just a starting example. We'll go through and see exactly how this works in a moment. But this is going to be kind of the the punchline of this section, right? If we could take a matrix and we can row reduce it into a triangular form like this, then calculate the determinant of the triangular matrix. That's much quicker than doing a full cofactor expansion on a matrix like a 4 by 4 or 5 by 5 matrix. Much quicker to use row reduction and then calculate the determinant. Now, the determinant of the row reduced matrix may or may not agree with the determinant of the original matrix. That's yet to be seen, but this is the idea. This is the general idea kind of up front. Okay, so let's prove that this is true. Let's prove this theorem for upper triangular matrices. Okay, we want to show that if A is upper triangular, then the determinant is the product of the diagonal elements, the diagonal entries. Okay, so let's go ahead and prove this. So this is going to use the definition of the determinant, which we saw was recursive, right? So the determinant definition was recursive, right? So you would start with the larger matrix. The determinant of that is identified using submatrices, which themselves are identified using submatrices. So there's a recurrent nature to that definition. And so we're going to go ahead and use induction to prove this theorem as well. Okay, so we're going to use induction to prove this. And so we'll start with our base case. We'll let n equal 1. Right, so this is the base case. So in the case of n being A being a 1 by 1 matrix, we know that there's just one entry, and we know that the determinant is A11. Right? Okay, and so that gets us our base case. It's obviously A11 is the diagonal element, right? Okay, and then let's assume, so we'll let n be greater than 1, and assume that for any upper triangular n minus 1 by n minus 1 matrix, we have the induction hypothesis. So assume that for any n minus 1 by n minus 1 submatrix, or well, we'll just say matrix B, that the determinant of B is equal to B11, B22, dot, 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 Bn minus 1, n minus 1. Okay, so that's the induction hypothesis. That's what we're going to assume. Okay. All right, then consider A n by n. Okay, so A is n by n. Right, so the determinant of A, right, let's just write it out. It's going to be an1 plus an2 plus dot, 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 plus ann. Okay, right, that's just the definition. And what is this going to be equal to? Well, this is, remember the matrix is upper triangular, right? So this is going to be equal to 0 times an1 plus 0 times an2 plus dot 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 plus an, well, let's say actually, let's make it 0 times a n minus 1 and an n minus 1. Sorry about that. Okay. And plus, now the last entry is the one that's non-zero, right? Because this is the nth row, so it's the bottom row of the triangular matrix, and so that'd be a and n. Okay, and so this is the one that matters in the determinant of A. These are all 0, notice, right? The entries are all 0 along the bottom row, right? So remember what we're dealing with here. We've got 0, so we've got, you know, some A11, A22, dot, 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 ANN. These are all 0, right? So the first n minus 1 entries of the nth row are all 0. That's what you're seeing reflected here. And then this ANN is the only one that's not 0 in the nth row. Okay, and so specifically we can say because a n I equals 0 for I less than n, you know, since A is upper triangular. Okay, so bottom line takeaway here is that the determinant of A, you know, in this case, is equal to 0 plus dot 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 plus 0 plus ANN times script ANN, right? Which is equal to ANN times negative 1 to the n plus n times the determinant of the NN submatrix. Okay. All right. So that's in an upper triangular. That's basically what happens here, right? And so we know that this is just equal to ANN, and now notice n plus n. That's 2 times n, right? So this is an even value. So this is just 1, and so it's ANN times the determinant of the submatrix ANN. Okay. Okay. But notice here that this submatrix ANN is n minus 1 by n minus 1. Right? So note ANN is an n minus 1 by n minus 1 matrix. Right? And so what does that mean? Well, that n minus 1 by n minus 1 submatrix is upper triangular also, right? Because A is upper triangular. And so by the induction hypothesis, so ANN is n minus 1 by n minus 1 matrix, and it is upper triangular, right? Is that clear? Let's make sure that's clear. All right, so here's your n minus 1 by n minus 1. So I've got A11, A22, all the way down to ANN. Right, now what I've done is I've cut out the nth row and the nth column, and so what I'm left with is this submatrix, which is itself upper triangular, right? These are all zeros, and these are all, you know, everything above the diagonal may be 0 or non-zero, but everything below the diagonal is 0. And so this n minus 1 by n minus 1 matrix is itself upper triangular. Okay. Okay, and so by the induction hypothesis, what do we have? Well, what we have is that the determinant of the NN submatrix is equal to A11, A22, dot, 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 A, and then this is n minus 1, n minus 1, right? These are the diagonal entries of that submatrix. Okay, and so that implies, right, so remember this, we've got our determinant A equal to ANN times the determinant of the NN submatrix, which is ANN times this product A11, A22, dot, 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 AN minus 1, N minus 1. Right? And then you can, of course, see that this just adds the nth diagonal element to that product. Right? So it's just equal to A11, A22, dot, 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 ANN. And that is exactly what we want to show. Okay? So we've shown that for any upper triangular matrix, the determinant can be identified very quickly by simply multiplying the diagonal entries. All right, so let's do an example real quick. We've done examples already, but let's make sure we're clear on this. So find the determinant. All right, find the determinant of A equals 4, 2, 0, 1, 0, 3, 9, 6, 0, 0, negative 1, 5, 0, 0, 0, 7. Well, the determinant of A in this case is just the product. Notice it's upper triangular. That's the key, obviously. Upper triangular matrix, so we can multiply the diagonal entries. So 4 times 3 times negative 1 times 7. Okay, that's going to be what? 12 times 7 times negative 1, so equals 84 negative. Okay. All right, so this gets us part of the way, right? The next thing we need to be able to do, next thing we need to be able to say is that row operations do not impact the determinant of the matrix. Or, more likely, if they do, how can we account for it? Okay, how can we account for it? So, how do row operations impact the determinant? That's the big question here. Well, this has been worked out, obviously, and here's the theorem telling you exactly what you need to know. So let A be an n by n matrix with determinant determinant A. Let C be a scalar. Okay, a real number. Okay. So let's talk about each of the row operations separately. We'll start with row op 1. Okay. So if row operation 1 is, you take a constant times a row, and that becomes the new row, then the row operation 1 applied to A and the determinant of that matrix is equal to the constant times the determinant of A. Okay, so does that make sense? So we start with A. If we apply this row operation to A, then the determinant of the row operation, A on A, that resultant matrix, that determinant is equal to the constant times the determinant of A. Okay, so basically the effect here, when we multiply by a constant, we do that row operation, the impact it has on the determinant is basically exactly the same. Like we multiply the determinant by the same constant. Okay, so that's that one. The second row operation is kind of the really messy one, so we'll call that row operation 2. So if row operation 2 is you've got row J being replaced by a constant times row I plus row J. Well, in this case, surprisingly, the determinant of the resultant matrix is the same as the determinant of A. This row operation actually has no effect on the value of the determinant. A little surprising, right? A little bit surprising. but it turns out to be the case. And then finally, the third row operation, R3, if that operation is basically the swapping of two rows, swap I and j, then the determinant of the resultant matrix is equal to the negative determinant of A. Okay? So this is interesting. These are all very kind of simple things to account for. So basically, if you multiply a row by a scalar, then you have to multiply the determinant of A by the same scalar to keep them aligned. You get this one for free, right? So this is the one that you would think would really screw up the determinant, but it actually has no effect on the determinant, surprisingly. And then swapping rows causes the sign of the determinant to flip. So negative, and then another negative would make it a positive, and then another negative would make it negative. So the sign will flip. So if you do 2 or 3 row exchanges, then you have to keep track of 2 or 3 sign flips for the determinant. Okay. All right. Let's see a couple of simple examples where this kind of comes into play. So these are really simple examples. So let's say that A is equal to 2, 3, 0, 0, 3, 4, 0, 0, 1. Okay, now notice this is upper triangular because I want to be able to calculate the determinant really quickly. So the determinant here is 6. 2 times 3 times 1 is 6. Okay, now A is row equivalent to a matrix B, where B is equal to, instead of 2, 3, 0, let's multiply that by 2 and make it 4, 6, 0, and then 0, 3, 4, 0, 0, 1. Okay, so what have I done here? To transform A into B, what I did was I did a row operation 1. I did this guy, didn't I? And C was equal to 2. So I multiplied row 1 by 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 0 is 0. Now what's the determinant of this resultant matrix? Well, it's 4 times 3 times 1. So the determinant of B in this case is 12. Right, so notice that that is indeed 2 times A. So the determinant of B is equal to 2 times the determinant of A. Right? Remember, that's how we converted A into B. We did 2 times row 1. Right? And so you can see that that one seems to work in this case. Okay, one more example. Let's do another example, kind of a simple one, just to see how these pan out. But let's let A equal 2, 3, 0, 0, 0, 1, 0, 3, 4. Okay, what's the determinant of A? Well, this is an upper triangular, so we can't use that very simple. We can't just multiply the diagonal entries. So, but we can do a row expansion across row 2 because everything's 0 there except for entry 2, 3. So let's do a row expansion across row 2, right? And so that's going to be equal to, it's going to be 0, right? 0 times the submatrix 2, 1 plus 0 times the submatrix 2, 2 plus 1 times negative 1 to the, this will be the 2, 3 entry, so 2 plus 3, times the submatrix you get when you kind of cross those out, so you get 2, 3, 0, 3. Okay, so it's negative 1, and then this is a 2 by 2, so it's 2 times 3 is 6, minus 0. So the determinant here is negative 6. Okay, so that's relatively quick and easy to discover. But notice that A is row equivalent to B, where B is equal to 2, 3, 0, 0, 3, 4, 0, 0, 1. What have I done to A to get this? Well, I just swapped these rows, didn't I? I swapped rows 2 and 3. Right? I made the 0, 0, 1 down at the bottom and the 0, 3, 4 in the middle. right? And so what is the determinant of B? Oh, it's 2 times 3 times 1, so it's 6. Okay, and so you can see here also that the previous theorem indicates that when you swap a row, the sign of the determinant flips, and that's exactly what you see here. You see that the determinant of B is equal to negative determinant of A. Okay, so the row operation had the expected impact. All right, very good, very good. Okay, and so we'll do an example here in a moment where we kind of run through this whole deal. But let's think about what is implied by this. What's implied by the connection that we've just discovered between row operations and the value of the determinant? Okay, so a few things are implicit here, and a couple of these we'll call out formally in a second, but what does this imply? Right, what connections can we kind of draw from this? Well, one of the things that kind of becomes clear is that if A is going to have a row that's all 0 in reduced row echelon form, I mean, that's basically going to mean that this, that A has a determinant equal to 0, right? So if A has a row that is all 0 in RREF, then the determinant of A is 0. Right? That's just because, if you had a situation like this, well, this is upper triangular, and 2 times 3 times 0 equals 0. Right? So that seems like, if you have a system, well, if you have a matrix, we won't go to the system yet, but if you have a matrix where one of the rows produces like an independent variable, then the determinant must be 0. Another thing that this implies is that if A has 2 identical rows, then the determinant must be 0 as well. Right? The determinant is 0 in those cases as well. 2 identical rows is the same thing as basically saying that one of them is going to be all 0, right, in reduced row echelon form. Okay. All right. And there are other things that are kind of, quick corollaries of this theorem, this reduced row echelon form theorem, or this row operation theorem in the relationship to the determinant. Here's another one, which we'll state as a corollary. Okay, if A is an n by n matrix, if A is n by n and C is a scalar, a real number, then the determinant of C times A is equal to C to the n times A. Well, this one is not completely obvious, but you can think about it in a certain sense. Like, so if I start with A, then I can multiply row 1 by C to get A1, right? So this would be like row 1 is replaced by C times row 1. Right, and then that means the determinant gets multiplied by C. I can do it again to row 2, and that's going to be like row 2 is replaced by C times row 2. And then I can do it again to row 3. Let's say it's a 3 by 3 matrix. Right, each time I'm impacting the determinant by a factor of C. Right, so if I have n rows, then I have to do this n times. And so the impact to the determinant is C to the n power. In this case, it'd be C cubed if this was a 3 by 3 matrix. Right, and then the effect of all these row operations is really just C times A, isn't it? All multiplying all n rows by c, right? So this is not a proof, but this kind of shows you how this like quickly follows from the previous theorem. Okay, let's take a look at an example where we actually do the row reduction and see how it all kind of feeds into the calculation of the determinant. Okay, so let's let A equal 0, -14, -8, 0, -14, -8, 1, 3, 2, and then -2, 0, 6. Okay, so not an upper triangular matrix, but you know, a 3 by 3 matrix. So we could calculate the determinant using the 3 by 3 method or by using the cofactor expansion method. But let's just do row reduction on this and see how the determinant falls out. Okay, so we'd say A is equivalent to, I'm just going to start by swapping, well, okay, we'll start by actually, we got to, kind of the key thing here is bookkeeping. Like, just don't lose track of the operations that you've done. So let me be careful here. 0, -14, -8, 1, 3, 2, -2, 0, 6. Okay, the first thing I'm going to do is I'm going to swap these two rows. I'm going to swap row 1 and row 2. Okay, and so when I do that, it's 1, 3, 2, 0, -14, -8, -2, 0, and 6. Now, what does this row operation do to the determinant? Well, it flips the sign, so I'm just going to make a note there. Okay. Next thing I'm going to do is I'm going to multiply row 1 by the number 2, by the scalar 2, and I'm going to add it to row 3, and that's going to become my new row 3. Okay, so basically I'm going to get a 0 down here. Okay, so when I do that, I have 1, 3, 2, 0, -14, -8, and then 0, and 6, and is that a 10? Yep. So 2 times 2 is 4, plus 6 is 10. Okay, now what impact did this have on the determinant? This is row op type 2, which we found to have no impact on the determinant, right? So I'm just going to denote that by multiplying by 1, just to keep track of it. So then what should I do? Well, the next thing, we need a pivot here in row 2, so I'm going to multiply by 1 over 14, -1 over 14. Okay, and so I'll have 1, 3, 2, and then on the bottom I'll have a 0, 6, 10, and then in the middle I'll have 0, and then a 1, and then this is going to be 8 over 14. So 8 over 14, we can reduce that to 4 over 7. Okay. And did we have to pay for that? Yeah, we do, right? That's going to be multiplication by a scalar, and so we have to actually multiply the determinant by the same scalar, so -1 over 14. Okay, so let's keep track of that. Okay, and the next one I get for free, which is I'm going to take -6, and I'm going to add that. I'm going to multiply -6 by row 2 and add that to row 3, and that's going to become the new row 3. So I go 1, 3, 2, 0, 1, 4 sevenths, and then 0, 0. And then what do I have here? I've got 6 times 4 is 24 over 7. And so adding 10 to that, I get 46 over 7. So pause and confirm that calculation, but that's what you get. And so here again, I get that one for free. Okay, and now I can say I'm done for our purposes, right? Because I've got this in upper triangular form. Okay, and so I'm going to call this matrix B. Okay, I'm going to call this matrix B. Okay, and so the theorem says that the determinant of B is equal to all of these things times the determinant of A. So just kind of looking back here, I got a -1 times a 1 times -1 over 14 times another 1. All of that times the determinant of A. All right. Okay, so it's very important to keep track of this. So these are the things, these are the impacts you've had on the determinant via your row operations. Right? And so you can just kind of write out this equation here. Now the determinant of B can be pulled off of this thing really quickly, right? And so that means what? 46 over 7 is equal to, I'm just going to get rid of all of this stuff that doesn't matter here. So 1 times 1, those don't matter. Negative times a negative. So this is 1 over 14 times the determinant of A. Okay, and so I can quickly calculate the determinant of A by just solving this equation. So determinant of A is equal to 14 over 1 times 46 over 7. And so this would be 2 times 46, which is 92. Okay, so I've calculated the determinant of this 3 by 3 using this method. Right now, in the case of a 3 by 3, it's questionable whether this is faster. But in the case of a 4 by 4, there's no question that this is faster. So there's no question that using this approach, using reduced row echelon, just row reducing till you have an upper triangular matrix, if you can do that, you can do it relatively quickly. It's much, much quicker. Right? The danger in this method is people lose track of what the row operation impact to the determinant is. And so keep track of that, whatever sort of, whatever notation you have to employ in order to keep track of that. That's kind of the key. Okay. Excellent. And so one last thing we want to talk about is this theorem. So this theorem is going to give us an alternative way of determining whether an inverse exists. And it's going to via the value of the determinant, right? And so an n by n matrix A is non-singular, right? It's non-singular if and only if the determinant of A is non-zero. Okay, this is something that I think kind of falls out of the previous theorem as well. I think you can almost catch this idea as you're thinking through some of those connections. It's all related to, basically like related to the rank of the matrix. Right. So if the determinant is 0, that means once you put it into, let's go through the proof actually. We'll go through the proof. Instead of me kind of rambling about it, let's just prove it. Okay. So we're going to let D, we're going to use the notation D to denote the matrix A in reduced row echelon form. So we're going to let D equal the reduced row echelon form of A. Okay. Now we know D is unique, right? There aren't two distinct D's that are equivalent to A and also in reduced row echelon form. There's only one. Okay. And so a key thing here to note is that we know that row operations cannot convert a matrix with non-zero determinant to a matrix with 0 determinant. Right, so I'm going to state that. That kind of falls out of the previous theorem. So we know that row ops cannot convert a matrix with non-zero determinant to a matrix with 0 determinant. Right, now hopefully that's clear, but let's just make sure that that's clear, right? So here's the theorem, right? If A is an n by n matrix with determinant A and C is a scalar, right? Now we know C is a non-zero scalar actually. The row operation, if you go back and you look at the definition of these row operations, C is C is required to be a non-zero scalar, right? It doesn't fly for C to be equal to 0. Right, but for non-zero C's, this is going to be multiplying by a non-zero number, so that can't make the matrix into a matrix with a determinant of 0, obviously. This multiplication by a non-zero number never results in 0. Same thing here. This is a negative, right? So the 3 row operations that are permitted are not going to convert a matrix with a non-zero determinant into a matrix with a 0 determinant. That's important to understand up front. Okay, so that being said, I guess to kind of spell it out, then we would say that the determinant of A and the determinant of D are either both non-zero or 0. Right, so that's the key, right? So these two things are very important. Okay, make sure you understand those, otherwise it's in one ear, out the other, right? If you can see that this is the case, then kind of the proof is obvious in some sense. Right, so let's go the one way first. Okay, we'll go the one way first. If A is non-singular, right, if A is non-singular, then we saw previously that non-singular matrices are row equivalent to the identity matrix, right? So that means the reduced row echelon form of A, which is what we call D, is equal to the identity matrix. Okay. Now, obviously, the identity matrix is a upper triangular matrix with all 1s on the diagonal, and so clearly the determinant of D, which is the same as the determinant of the n by n identity matrix, is equal to 1. Right. And so obviously the determinant of A is non-zero, since the determinant of D is non-zero. Okay, so that's one direction. Okay, that's the one direction. What about the other direction? Okay, let's go the other way. Okay, so an if and only if statement. So let's go the other way. Let's assume that the determinant of A is non-zero, and we'll show that that implies that A is non-singular. Right? So assume the determinant of A is non-zero, then the determinant of D is non-zero, right? By our earlier reasoning, of course. Because D is upper triangular, right? D is upper triangular. This is, of course, due to the reduced row echelon form, right? It means it's upper triangular. And because D, has a non-zero determinant, that's going to imply something about the diagonal entries, right? So because D is upper triangular and is a non-zero determinant, all the main diagonal entries are non-zero. They must be non-zero. Right, now imagine, right, if I have some matrix, A11, A22, ... ANN, right? If any one of those is 0, then the determinant is automatically 0, right? But we know that the determinant is non-zero. That means none of these can be 0. Okay? So if all the main diagonal entries are non-zero, and the matrix is in reduced row echelon form, as we've assumed, then they are all pivots. Then all the diagonal entries are pivots, right? And what does that mean? Well, that means that the reduced row echelon form of A, which we call D, is the identity matrix, right? And so that means that the matrix is non-singular. Okay, so the matrix is non-singular. Very good. Kind of goes both directions very easily. Very easily. Simple proof. kind of just a lot of sort of like recalling what previous theorems have said and sort of chaining them together. Okay, and something that I don't think we've said but follows really quickly from this, and we won't prove it, but I'll state it. If you haven't already caught this or thought this through, if we let A be an n by n matrix, if A is an n by n matrix, then the rank of A is equal to n if and only if the determinant of A is non-zero. Yeah, so that kind of follows very quickly from the previous statement. Right, so non-singular matrices must have rank n, and so that follows right away from the previous. Okay, very good. All right, so I think we'll end this lecture here, and next time we'll get into additional properties of determinants. So some of the additional interesting features of this number called the determinant. So the first two sections here were kind of more about like, what is the determinant? How do we calculate the determinant? And then this section has been a little bit more about like, okay, practically speaking, how should we calculate the determinant? And so what's coming up next is like, what's it all good for? Like, what does this thing tell us, right? So, yeah, so we'll leave it there, and we'll pick it up next time. So take care. Till next time, take care.